Okay, right. So today we are going to discuss about some useful digital circuit components. So this is not going to be a very lengthy one, and we are going to do some faster questions. Right. So let's move on. So here we are going to cover some types of digital. What are the different types of digital logic circuits? Some of the useful digital circuit components and use of digital circuit components in the computer. So just few examples only we are going to discuss. Let's first discuss the type of digital circuits. We can differentiate or we can categorize digital circuits into two types, that is combinational digital circuits and sequential digital circuits. So the combinational digital circuit means the result of the or the result or the output does not depends on the time or memory. Basically, if it is combinational digital circuit, it doesn't have a memory or the output does not depends on the current value or the previous value. So then we call it combinational digital circuit. For example, when we add two numbers, we do not rely on memory. Whenever if someone asks what is 5 plus 7, it is 12. It doesn't matter what is your memory is. Okay. So that kind of things are called combinational digital circuit. Then the sequential digital circuit means circuits or digital circuits that depends on the memory. Either it depends on the memory or basically it is keeping something in the memory. So then we call it sequential digital circuit component. We will first look at the combinational digital circuit components. So under combinational digital circuit, that is the circuit that does not depends on memory, we are going to discuss these four type of components: uh, adder, decoder, multiplexer, and encoder. Okay, so let's take one by one. So there are different usages. We'll come back to the usages later, but we'll take one by one without wasting any time. First, we are going to look at the adder. So adders are used to add binary numbers. Okay, so we can use adders to add binary numbers. We know how to add binary numbers. For example, if you have these two numbers, and if you want to add those two numbers, we know that 0 plus 1 is 1, 1 plus 1 is 2. So I will just take the pen. Just 1 minute. Right. So we know that 0 plus 1 is 1. There is no carry. Carry is 0. And 1 plus 1 is 2. 2 means we are not keeping anything. We are giving that 2 to the other side. So that means there is a carry of 1. So that carry is there. Then that carry and this 1 plus and 0 is again 2. 2 means 0. The carry is 1. Here nothing is there. That is 1. No carry. Then here we have 1 and 1. 1 means 2. 2 means 0. Carry 1. Then we have 1. So that is how we do binary addition. Now let's see how to design a circuit component to carry out or to execute this kind of summation. Right? This kind of summation. So for that we have a digital circuit component called adder. And so adders are capable of adding binary digits, right? Not entire thing by as a chunk, but one by one. For example, these two, then these two, then these two, these two, these two. Anyway, when we are adding, we have to add like that because we never know how much we are going to get as a carry. Therefore, we have to add from right to the left. Right. Now let's see what are the type of adders we have. We have half adder, then we have the full adder, then we have the ripple carry adder. So let's take one by one, starting with half adder. Half adder is used to add 2 bits, right? So it can be used to add 2 bits. If there is a carry in from the previous adder, it must be used twice. So that is why we call it half adder. Basically, it does the job halfway. So therefore, when we are using the half adder, we have to use it twice. So then you can see half plus half is 1. That is why we call it half adder. So when we are looking at the half adder, you will see that it has some issue also. Okay, right. Now let's first look at the half adder. Right. So this is the truth table for adding bits or binary digits. So when we have both 0, the sum is 0, there is no carry as well. When just one digit is 1, the sum is 1, still there is no carry. Again, it can be B is 1 and A is 0, or A is 1 and B is 0. Still the sum is 1, but still there is no carry. So there is a carry only when both are 1. Right? So that is when both are 1. Now the sum is 0 because 2 means 0, but we are now having a carry 1. So that is why we have 0, 1. Right, so you don't have to memorize this, it's very straightforward. When both are 0, sum and carry is 0. When at least one is 1, sum is 1, carry is 0. When both are 1, that means both inputs are 1, the sum is 0 but the carry is now 1. Okay. So for example, this scenario is something like this scenario. Now you can see sum is 1, carry is 0. Right. So this scenario. So this 1 scenario is something like this. Sum is 0, but the carry is 1. Okay, right. So that is the truth table for half adder. Half adder. This is how you represent the half adder as a block diagram. Right? So you just draw a square or something like that. Two inputs. You can have two inputs in this way or that way. It doesn't matter. Then this is your sum. This is your carry. Right. So you have two inputs. So it's something like these two. Two inputs, something like these two, then the sum and the carry. Okay, right. So this is how we are going to do the summation. Actually, there's a small mistake in my slide. Actually, I was a little bit hurried to do that. Actually, this must be your sum. Okay, this must be your sum. So this line must be somewhere here. Okay, right. Anyway, so when we are doing the addition, so if you look at closely this part of the truth table, you will see that it is exactly the XOR gate, truth table for the XOR gate. When things are different, 1. When things are the same, 0, 0, it's 0, 1, 1, 0. This is the XOR gate. So therefore, to get the sum, we can simply use the XOR gate, right? So if you input those two, so this should be A and B actually, A and B. So if you just get those two to the sum XOR gate, you are going to get the summation because this is true. This truth table is for XOR gate. Now, if you forget about this part and look at A, B, and C out, now you will see that it is your AND gate, right? 0, 0 is 0, 0, 1 is 0, 1, 0 is 0. When both are 1, only 1. So therefore, to get the C out, you can use a AND gate, right? You can use AND gate. So that means if you have XOR gate for the sum and AND gate for the carry, now we are done. We have the half adder. Half adder. So this is the circuit for the half adder, right? So this is the circuit for the half adder where we have for the sum we need XOR gate, for the carry out we need a AND gate because there is a carry out only when both are 1, but there is a 1 for the sum there is 1 when both only 1 is 1. When both are 0, there is no sum and there is no carry as well. And both are 1 also there is no sum. So therefore we can go for the XOR gate. So that is very straightforward. So you can use XOR gate for the sum part to get the sum. You can use AND gate for the get the carry out. So you can see sometimes yes we have only two inputs, but there are most of the time we have three inputs, right? So that is your X, Y, or A, B, and the carry coming from the previous summation, right? Carry coming from the previous summation. So therefore, most of the time what we need is three inputs. That is your A, B, and the carry coming from the previous guy. But in this half adder, we have only two inputs and the outputs are sum and carry. So therefore, this one is little bit restrictive when it comes to adding this kind of numbers where there is a possibility of carry. And of course, most of the time you will get a carry as well. So therefore, this adder is doing only half of the job, right? Because it can add only two numbers, whereas sometimes when of course we are adding these two numbers, but while we are adding those two numbers, sometimes we have to add three digits, right? So digits from your A and B as well as the digit coming as a carry. So therefore, what we really need is either three inputs, or we can use this if you apply this half adder twice. So that means something like this. So first you add these two numbers, then you get a summation, then you add that again with the previous carry. So that means you add once, then that sum is again add one. So that means you have to use this adder two times, right? So if you use this adder two times, you can add this particular line. Again, if you use this adder two times, you can add this line. But you have to use two times, that means this is doing only half of the job. So that is why we call it half adder, because we have to use this adder two times to get one set of numbers, so one line to get summation, right? Because it can't add three numbers together, right? So that is why we call it half adder. To solve this, people came up with a concept called full adder, right? Full adder. There we have three inputs, right? So there we have three inputs, whereas in the previous case we had only two inputs. So if I draw the block diagram for the full ladder, it will be, so there will be three inputs, A, B and carry in. Then you have two output, sum and carry out, right? Sum and carry out. So that is what we need. Three inputs, A, B and carry in, and two outputs, sum and carry out. So that in that case, when we want to add numbers, we can straight away add those numbers, because now we have three inputs rather than two inputs. Okay, right. So this is how you do this. Now this is the truth table. The truth table you don't have to memorize. It's very easy, right? So when now these are the three inputs now, A, B and the carry in, right? So three inputs. When all three are 0, sum is 0, carry is also 0. When just one is 1, the sum is 1, carry is 0. Now you can see this is also, now here there are two ones, that means sum is 0, carry is 1. Here also just one input is there, sum is 1, carry is 0. Two inputs are 1, sum is 0, carry is 1. Here also two inputs are 1, sum is 0, carry is 1. Here all three are 1, that means sum is 1, carry is 1, right? So that anytime you must be able to draw this, anytime without memorizing you must be able to draw it, right? Now let's look at the circuit. Let's look at the circuit. It's very easy, right? So if you understand the logic, you can draw it by yourself, right? First you have to remember or understand the half adder, right? Half adder. Then you can, from the half adder, you can draw the full adder. Okay. So now let's see how to come up with the full adder. So this is how you draw it. I will explain it using the one note. Right. So assume this is my, I will use this one. Say this is my half adder. Right. So now I have three inputs. Right. One, two, three input. That is A, B, and carry in. And I have two outputs. That is sum and carry out. Now, since I need to add three numbers, what I am going to do is first I am going to add these two numbers. Then that summation I am going to add with the other number, right? We know how to add two numbers, we have to use the XOR gate. So let's have XOR gate here, right? So that is my A and B, right? Then I need another XOR gate because I am going to do another summation. For that I need another XOR gate. For that I have this summation and also I need the Cin. So let's have the Cin like this, carrying from the previous step, and this is going to be my sum. So that is very logical. So you add these two together, right, using the XOR, then you add to that sum, you are adding the C in, right? So now you get the sum, right? Now we have to look at how to get the, now we are done with the sum, how to get the C out. Now we know that the AND gate give us the carry out, because when both are one only one, right? Both are one only one means, because when both are one only there is a carry out. When both are one only there is a carry out. So therefore we need AND gate. So here we had AND gate previously. So let's have the same AND gate. And let's have the same AND gate to give the, if there's a possibility, if there's a carry out here, you will get it from this AND gate. But not only there's a possibility of carry out when you are adding these two, this summation with C in as well. So therefore we need another AND gate to get that possible carry out, because here also when you are doing these two also there's a possibility of carry out. When you are adding these results with C in, there's a possibility of carry out. So this AND gate will give you the first possibility, this AND gate will give you the second possibility. Then if there is a carry out in this summation or this summation, there is a carry out. So O, right? If there is carry out here, O, if there is carry out here, there is a carry out. Therefore what we need is a O gate. What we need is a O gate to get the carry out. Now we call this the full ladder, right? So why? Now we have three inputs, right? A, B and C in, and we have the two outputs, sum and carry out, right? Sum and the carry out. Now we can straight away add numbers. For example, if I want to add 1 0 1 1 with 1 0 1, right? So initially this 1 and 1 will be your A and B, and there is no carry in, so this will be 0. Then you will get 1 1 is 0, there is a carry of 1. So that means your sum will be 0, your carry out will be 1, right? So then you are done with that. Then your A will be 1, B will be 0. Assume this is your A, B. Okay. Now your A will be 1, B will be 0. Now your carry in is 1. Right. Now again your sum is going to be 0. Your carry is going to be 1. So that means your sum is 0. Your carry is 1. Right. Now again you will be adding the numbers. So now A will be 0. Right. And the B will be 1, and your carry will be 1. Carry in will be 1. Now again what you get is sum is 0, carry is 1. Right? Sum is 0, carry is 1. So that means your sum will be 0, your carry will be 1. Now for the final time, right? Now again your A has 1, but your B is now 0. B is now 0. Now your carry is again 1, right? Carry is again 1. Now again it will be sum as 0, carry is 1. So again your sum will be 0, carry is 1. Now these A and B values are 0 for these things. Now again it will be adding 0 0, right? But there's a carry, and again it will be 1. Sum is now 1, going to be 1, but your carry is going to be 0, and you are done. You are done. So that is going to be your answer, 1 0 0 0 0 0. Let's see if the answer is correct. 1 1 is 0, 1 and 1 is 0, 1 1 1 0, 1 1 is 0, 1 1 is 0. C is correct, right? Right, so that is how it works, right? So it's very easy to understand full ladder. Now you can see you don't have to use it twice. When you are adding one column, you can just add it in single passing. So that is why we say it's a full ladder. But earlier case, when you are adding this kind of a situation, you had to use the half adder twice. That is why it was called half adder, right? So now you must be able to compare these adders together, right? So that is where you get the full understanding, right? Now let's see, if you want, you can draw your full ladder using the half adder as well, right? So if you want, you can draw the full ladder using half adder, right? For example, this is your full ladder, right? This is your full ladder where you have the two XOR gates and two AND gates and the OR gates. Now if you closely look at this, you will see that this is one half adder and this is another half adder, exactly half adder, right? Exactly half adder. So therefore, if you want, you can draw your full adder using half adders. That is, you can say I need a half adder, right? Half adder. I need another half adder, right? For the half adder, you need A and B or X and Y or whatever. From there, you are feeding to the other half adder and you are getting the carry in from the previous here, and you are going to get the sum here, right? So you are done for the sum. But now we are going to do, we need a, now remember half adder has two output, the sum and the carry out. So this is your first carry out. This half adder also giving you another carry out. For those two, now remember this is our one half adder, this is another half adder. Now we need the OR gate separately, right? Separately, and this is going to be my carry out. So that is how you draw the full ladder using two half adders and OR gate. So likewise, you must be able to visualize it different ways, right? So now you can see that if you have two half adders and OR gate, you can create the full ladder from that also, right? Full ladder from that also. So that is another way of looking at the full ladder, right? Right. Now we are moving to the final type of adder, that is called the ripple carry adder, right? Ripple carry adder. So ripple carry adder is not a new adder actually. It is just a interconnection of full adders in a serial manner, right? Because we know that when we are adding numbers, right? So say this is my A, this is my, assume that this is my A, this is my B. So if I have a full ladder, first time I can add these two numbers, assuming that there's no carry once. Then next time I will be inputting these three numbers. This is your carry from the previous one. Then you will be inserting these three. Then you will be inputting these three, right? These three. So the next time it will be 0 0, but you need something like this, right? So that means if I have just one full ladder, because it has three inputs X, A, B, and carry in, and it has two outputs sum and carry out. Now, once I can send these three numbers here, right? So the next one I can send these three numbers again, but we have to make sure that the previous C out is your current C in, right? But again, you can see that I can use my full ladder, but I have to use it. For example, if there are 8 bits, if you add in 8-bit numbers, right? Something like this, 1 1 0 0 1 0 1 1. So if there are 8-bit numbers, you have to use this adder not 8 times, actually you have to use it 9 times, because final step also there's a possibility of overflow, but in that case we say that there's overflow. In that case usually it's a garbage value. So because you must not have or carry out at the last step. If there's a carry out in the your leftmost bit, if it is a full capacity, that means your answer is not is actually bigger than what is capable of keeping in 1 byte. Okay, so therefore if you have 8 bit, you need to call this adder 8 times, 8 times, right? So rather than doing it, people came up with another idea, that is, why can't we or why don't we assemble those full ladders in a sequential manner going from here to here, right? So rather than sending these numbers to the same ladder, now we can send these numbers to different adders, right? Different adders. Of course, you can't send them parallelly, right? You can't send them parallelly because you need to calculate the rightmost bits to do the next bit, because then only you know the carry out, right? So once you do this, you can go into the next one. Once you do this, you can go into the next one. So therefore, though we have assemble those in parallel serially, it will work like this, right, from right to the left. So ripple means something like a wave, right, something like a wave. So it executes like a wave from right to the left, right to the left. So that is why we call it ripple carry adder, right? So then we are not using the same full adder more than once, but first we are going to use this full ladder, then the next full ladder, next full ladder. Likewise, if it is 8-bit number, the 8th full ladder will be used as the last time, right? So it will give you little bit easier for the designing of your arithmetic and logic unit, and also it will make it little bit faster as well. Okay, so therefore ripple carry adder is not a new thing. It is just full ladders assembled in a serial manner, so that it can keep on adding the numbers from add two numbers from right to the left, right, just like a ripple or wave. It will keep on giving you the so if you closely look at this, so here we are getting the sums, right, sums. So the first sum, second sum, third sum, etc. And each carry out is feed to the next carry in, right? So carry out from the first set of numbers is the feed for the carry in for the next set of numbers. Each carry out is feed for the next set of next full ladder. Likewise, the final carry out we don't care. Actually, if there is a carry out in the final step, that means the result is actually garbage, right? Result is garbage. And also for the first full ladder, the carry in is always 0, because you can see that here it is always 0. So that is always 0, right? So those are things you have to understand. For the first one, carry in is always 0. Last one, we don't care about the carry out, but we have to check if there is a carry out. We know that actually we have to check whether there is a carry out in the last one. If there is a carry out, definitely the answer is garbage, right? Answer is garbage. That means it has overflow. Okay, and first one of course the carry in is always 0, right? So those are small things you have to understand to better understand or perfectly sort of understand what is mean by adder. Okay, right. Now again, you must be able to look at it, visualize it in different ways. We know that we can draw a full ladder using two half adders, right? Two half adders. Therefore, now this is again the ripple carry adder drawn using different notation. That is the notation of half adders. Now you can see every full header has two half adders, and we have to have OR gate to combine the possible overflows. But you can clearly see something very interesting, that is here you need two half adders, here you need two half adders, everywhere you need two half adders, but for the first set of numbers, that is when for the this first half adder or for the first full adder, we since we know that this carry in is always 0, we can just use one half adder only, right? So that is very famous question in ICT papers, right? So for the first full ladder, actually for the first one we don't need a full ladder, just one half ladder is enough. But for the rest of the stuff, yes, we need full ladders. That means we need two half adders. Okay. So here why we just need one half adder, because there is no C in. Therefore, we just have to add two numbers only, 2 bits only. But here there is a possibility of adding 3 bits. So therefore, we need two half adders. Okay. So those are the small things that will make things more interesting and understandable. Okay. Right. Right, now we are done with adders. So adders are very simple to understand. Just you have to understand what is the issue with the half adder. Yes, full adder is a better thing, right? So because it had three inputs. Rather than using the full adder over and over, same full adder, we can assemble them as a serial thing and use it as a ripple or wave, so that it will make your implementation or the execution a little bit faster. Okay. Right, now we are done with the adders. Now we are moving to the second combinational circuit. Right, second combinational circuit component. So we call it decoder. Right, we call it decoder. So decoder is an interesting device or digital circuit component where you have n inputs, right? N inputs and 2 to the power n outputs. Right, n inputs, 2 to the power n outputs. But that's very important restriction. At a time, only one output can be on while all the others are 0. So there is another restriction when it comes to decoder. At a time, only one is 1 or one signal is on, all the others must be 0. So maybe next time this one is 1, then definitely all the others must be 0. So at a time, only one must be 1 while all the others are 0. Right? So that kind of a digital circuit is called decoder, or the digital circuit component is called decoder. Right? So decoders have a lot of usages in computer architecture, especially in memory accessing. Right? Especially in memory accessing, the CPU use, or the memory side has a decoder, so that it can we can say which memory address we want to access right now, because at a time we are not going to access two memory locations, right? So that means at a time, so there will be a decoder here, right? So at a time only one memory location will be enabled, so that is what we are interested in reading or writing, right? Because we are not interested of any other place, so that is perfectly naturally perfectly that will work for memory accessing, right? So the advantage of having a decoder is, now we have less number of inputs and more number of outputs. Now, for example, if you take memory, there can be, say, so let's assume just say 1 lakh memory locations, 100,000 memory locations. So now we want to enable, out of that 100,000 memory locations, which memory location we want to read. So we have to send that control signal. Now, how to send that control signals from the CPU or the processor to the memory? So if you have 100,000 memory locations, one option is have 100,000 lines coming from there, and that the relevant line will say, okay, you must be now one. But that is very costly, because having 100,000 lines from CPU to the memory is really costly. But if you have a decoder, because we know that decoder is capable of enabling or making only one location on at a time, or that means you are given that signal to that particular location while the others are just waiting. That is good. That is good, right? For example, at least it will reduce number of lines. Okay. For example, if you need, so just assume that if you need two, say four, if you have four memory locations, now earlier we need four lines, just now we need only two lines, because we know that 2 to the power 2 is 4, right? So definitely it has make it half of the costing, right? So if you have 8 memory location, what we need is only 3 lines now. If you have 16, we just need 4. If you have 32, right? If you have 32, we just need 5, right? So likewise, if you have 1024, what we need is just 10, right? So you can see 1000 to access 1024 memory locations, or to give the signal of out of 1024 memory locations, we want to give a signal to one of one of the location that we want to access that, but we just need 10 lines. We just need 10 lines, because 2 to the power 10 is 1024. Okay, so that kind of a device is called decoder, right? So we have n inputs, 2 to the power n outputs, only one output will be enabled at a time, right? So that is called that kind of a digital circuit called decoder. Now you can see it's making sense, right? For example, if you have something like 20 input lines, now I can have 2 to the power 20 memory location. Out of 2 to the power 20 memory locations, only one I can enable at a time. So that is a huge number actually. 2 to the power 20 is huge number, right? For example, if you take a calculator, so the first thing is you have to appreciate what is this, rather than just blindly looking at it, right? So if you have, let's say, go to scientific calculator. So So x to the power y, 2 to the power 20. Right, so now you can see I just need 20 lines, but I can access this much of memory addresses. How much is that? It's definitely one more than 1 million, right? More than 1 million memory accesses. Only one memory address will be enabled at a time, but I need only 20 lines. 20 lines. So 20 is not a huge value because I can access more than 1 million memory locations using that 20 lines. Okay, so that is why we have decoders, right? So that is why we have decoders, right? Now let's see how the now you must understand why we have decoders, and also it's okay that we in the memory we don't want to access two memory locations at the same time. Anyway, we will discuss that further when we are doing computer architecture. So that kind of situation, that is really good, right? That is really good. It will reduce a lot of wastage of our wiring requirement. Okay, now let's see how the decoder is implemented using digital circuits. Okay, how the decoder is implemented using digital circuits. Then we can identify depending on the size different decoders like 1 to 2 decoder when n equal 1, when n equal 2, 2 to 4 decoder when n equal 3, 3 to 8 decoder when n equal 4, 4 to 16 decoder, etc. Like 10 to 1024, etc. And again, if you need something like 10, then you have no other option. You have to go for 4 to 16 decoder, right? 4 to 16 decoder. Of course, you are not using all the 16 things, but because 3 to 8 decoder is not good enough because you have 10 different things to be accessed, right? So likewise, then you have to go to the next nearest decoder when you have that kind of a requirement. Okay, now let's look at how the simplest one, that is how the 1 to 2 decoder is created. Right? It's very simple approach. Right? It's very simple approach. Anyone can understand a decoder. That is, you just need this kind of a circuit. It's very simple circuit. Right? You just need one NOT gate. Right? One NOT gate. So this is how you represent it in a block diagram. There's one input, two output. But remember, only one will be when this is one, this is zero. When this is zero, this is one. Only one will be one at a time. Okay, only one will be one at a time. So this particular truth table will do it, right? For example, when input is 0, I want to make sure that this particular output is 1, the other output is 0. When input is 1, I want to make sure that my first output is 1, the zeroth output is 0, right? So how to implement this? It's very easy. You just have this particular circuit component. Now you can see that when I equals 0, I equals 0, your O1 is 0 because there is a NOT gate, O0 is 1. Right? When I equal 1, this guy is 1 and now this guy is 0. Now that is exactly what we want. Right? So when this guy is 0, this guy is 1, this guy is 0. When this guy is 0, this guy is 1, this guy is 0. Whatever the one you want, you can take. Right? So just one will be 1, the other one will be 0. So to enable either this one or this one, I just need one line of control, not two line of control. Right? So that is called 1 to 2 decoder. Right? So similarly, we can expand the same idea to 2 to 4 decoder. 2 to 4 decoder. It's very simple circuit. You need two AND gate. Now you need two NOT gates and four AND gates. Okay. So each combination is fed to the AND gate. For example, one AND gate will have both I0 and I1 as it is. Another one, both I0 and I1 are complemented or bar. Other two are going to have just one of the I1 is as it is, the other one is bar. Right? So those are the four combinations: I1 I0, I1 bar I0, I1 I0 bar, and I1 bar I0 bar. Okay, so I1 bar I0 bar means basically the stuff that is coming from here, the NOT 1, and here also the NOT 1, right? So that is I1 bar I0 bar. So I0, I1 is the stuff that is not going through the AND gate at all. Right? So likewise, you can see that all the possibilities are there. All the possibilities are there. So now this is going to work as a 2 to 4 decoder. For example, when both are 1, right? When both are 1, only this one is going to be 1, that is output 3, right? All the others are going to be 0. You know why it is? Because in AND logic, to be 1, both must be 1. Now, when there's at least bar here, or here both are bar also, when both are 1, when there's a bar, it is going to be 0, and 0 dot something is always 0. So, similarly, when both are 0, definitely this is going to be 1, because now both the zeros are made into 1s and all the others are going to be 0. Likewise, for different combinations, only one will be 1 all while the others are 0. That is definitely going to be. So it's a very simple logic. You know that for AND logic to be AND, both must be 1. So when we have this kind of a combination, for any input combination, only one is going to be 1 while all the others are going to be 0. Right? For each combination, there will be one output line 1, all the others are 0. Right? So when you think of how the AND logic works, you will see that yes, that is going to happen. Right? Okay, so that is called 2 to 4 decoder. So in that case, we can enable one of these output lines at a time using two inputs. So that is good. So rather than having two input lines, we have two input lines to enable one of the output lines at a time. Right? Only one is going to be enabled at a time, but for different combinations like 0 0 combination, one will be enabled, 0 1 another one, 1 0 another one, when both are one another one. So likewise, for different combinations, one of the output will be enabled or one, while the others are disabled or 0. Okay, right. So that is called 2 to 4 decoder. Now let's look at. Now we can extend the idea. Right, it's very easy. You can extend the idea to 3 to 8 decoder as well. Right. Only thing is now you have three inputs, right? So therefore we have three NOT gates as well, and we are going to have 8 AND gates, right? So then for different AND gates, we are going to feed different combinations, right? So all the possibilities are there. So one AND gate will be feed with no NOT gates, that is I0, I1, I2, right? So now everything as it is. The final AND gate will be fed all the things are negated, I0 bar, I1 bar, I2 bar, then all other AND gates are going to get all the other different combinations, where sometimes you have only one bar, sometimes two bars, etc. So all the combination will be covered. And again, when you have something like 1 1 1 in your, so actually there's a small mistake, there must be three bars here. When all are 1, definitely this one is going to be 1, that is I0, I1, I2, all the others are going to be 0, because there is bar somewhere in any all the other, at least one bar is there, that means definitely it's going to be 0, because when there's at least one 0, when you have AND, it's going to be 0, right? So similarly, when all are 0, uh, this guy is going to be the one, because it is inverting all three, all the others are going to be 0. So if you are familiar with the AND logic and in general how the logics work, you will see that that is really straightforward thing. You must be able to understand the decoder. Okay, so these are not big things. Right. So some people, when they say it is electronic, they get scared. Of course, yes. Analog electronic, you must be really scared of. But digital logic is, or digital circuits are really simple. So that is why early days people were reluctant to learn the electronic, but now people really enjoy learning electronic, because now we are doing a lot of digital electronic rather than the analog electronic. So the things are not that difficult now. Okay, right? Because these things we can easily understand. Right, now let's move on to the next device we are going to discuss. Now so far we have discussed the adder, the decoder. Now the third one is the multiplexer. Right? So without understanding these things, when you are moving to the other topics, for example, when you are doing the networking, we will be discussing multiplexing of the data. Right? So then if you don't know how the multiplexer works, then you are in sort of you have to blindly memorize those things. Right? right? So that is why we want to understand these things, because these things can be easily understood. Right? If something can be easily understood, why don't you understand it? Okay, right? Uh, so it will boost your confidence, right? Now let's see what is mean by multiplexer, right? So there's concept called multiplexer and demultiplexer. Okay, so multiplexers are used. Now remember, decoder is a complete different thing. We have n input, 2 to the power n output. Only one output is going to be enabled for different input combinations. Okay, now here when it comes to multiplexer, so this is how you represent a multiplexer basically, something like trapezium shape. So here we have 2 to the power n inputs, right? You can see 2 to the power n inputs are there, but there is only one output, right? So that is the difference. Now earlier n inputs, 2 to the power n outputs, right? So that means lesser number of inputs, more number of outputs. Here large number of inputs but just one output, in when it comes to multiplexer. Okay, so what does multiplexer does is, at different times, uh, in the output you can have different inputs going out. So that is called multiplexer, right? So I will explain it using example. Assume that here you are getting a bit stream like this 0. So I will be using the tab, right? So assume that uh, here you are getting a bit stream, say it's a data communication, something like 0 1 1 0 1 1, etc. Here we are getting 1 0 0 1 1 0. Here we are getting 0 0 1 0 1 1. Here we are getting, assume, just I am randomly writing 1 0 1 0 0 1. Right? So then we have now those are the 2 to the power n inputs. In this case, n is 2. That means I have 4 inputs. At a time, out of these 4 inputs, only one input will be in the output. For example, I can say currently my output is this one, that is 1 0 0 1 1 0. So that means I have enabled this line as the output. Right? So to do that, we have another concept here called control signals. Now you can see there are some signals coming there. So those are not the data inputs, those are called control signals, right? So these are the data inputs, these are the data inputs, whereas these are the controls. So by again the controls are also 0 1 values for different control signals. For example, I can say when both are 0, both control signals are 0, I would say now the output will be this one, right? When this one is 0, this one is 1, now the output will be whatever the input here, right? When 1 and 0, whatever the output will be something like this. So that means now the if it say it is if it is 1 0, now the output is going to be something like 0 0 1 0 1 1. So that means this one. So similarly, say that 1 1, the output is this one. So likewise, by changing the values of the control signals, I can make sure that one of these inputs are going to be the output. So that is called multiplexer, right? Digital multiplexer. It's something like this. You have so many input lines, right? You want to make sure that one of these input lines are your output line, right? So maybe now at that time it is tuned to I0. Maybe it is tuned somewhere here. Then it is I2 is going out from the outside. Others are block, sort of block. We don't care. Those inputs are what are the values of those inputs are. You are not interested. At a time you are only interested on one of the input because you are going to put it into the output, right? So if someone want to get this particular input, right? Say if someone want to get this particular input as the output, now it has to come to this position. So same thing, if someone want this one, right? So maybe we can call it I0, I1, I2, I3. So So 2 means basically 1 0. There's a way we can look at it. So we have to make sure that your control signals are 1 and 0. So this is your control signal 1, control signal 1. So control signal 0 and control signal 1. So then we say that okay, now we are tuned into the this particular, or the I2 input signal is your output now, right? So that is called multiplexer, right? That is called multiplexer. It is different from the analog multiplexers, right? Analog multiplexers are completely different concept. This is the multiplexer, right? Okay. Now let's see how to implement the multiplexer or the digital multiplexer. It's again not very difficult. It's actually really simple if you understand it. Uh, so this is what we are going to do. So this is the circuit that is going to work as 2 to 1 multiplexer. 2 to 1 multiplexer. You just need two AND gates and NOT gate and OR gate. Okay. So you need two AND gates, NOT gate and OR gates. So if you can understand 2 to 1 multiplexer, that is all good enough, because you don't want to, we don't want to memorize all the multiplexers. You can always refer to internet and get the circuit. But idea is to understand and appreciate why we have multiplexers and how it's work. Okay, right. Now if you look at this circuit, your output is going to be I0 dot C bar, right? C bar plus C and I1. That means I1C, right? So you can see that my output is going to be governed by this particular formula, right? C bar I0, right? We call them I0 and I bar I1. When we have two inputs, you just need one control signal. So you will see the pattern later. Right. So when you have two inputs, you need one control signal. When you have four inputs, you need two control signals. When you have eight inputs, you need three control signals, etc. Now in this case, you just need one control signals for the two inputs. Okay. So this is when you have, if you have a circuit like this, its output is going to be given by something like this. Now if you write the truth table for this one, so that we need I0, I1 and C, right? So there are again, because there are three inputs, we have 8 possible input combinations, right? If you substitute those values to this formula and get the output, you will get something like this. You will get something like this. Okay, right? So that you can always do it, right? For example, if you have 0 1 1, right? 0 1 1, so you can just substitute here. C is 0, that means 0 bar. I0 is 1, that is 1, plus C is 0, I1 is 1. So we know that 0 bar is 1, 1.1 is 1, 1 plus 0 is 1. You can see that output is 1, right? So likewise, you can assign those values and substitute those values and prepare the output values. Then you will see there's a definite pattern here, right? So that is how I have highlighted this. When the control signal is 0, right? When the control signal is 0, your output will be same as your I0 signal, right? So you have to draw the truth table and see by yourself. So 0 0 1 1 0 0 1 1. When control signal is 0, the output signal is same as your I0 signal, right? When the control signal is 1, your output signal is same as your I1 signal. So that is exactly what we need, right? That means if you have something like 0 0 1 0 and 1 0 1 1, so when control signal is 0, your output is going to have the I0 value. That means 0 0 1 0, etc. Okay, so this is for just one possibility. For all the possibility keeps on, it is going to happen always. When C is 0, your output is always going to have whatever the value in the I0, right? Whatever the value in the I0. So similarly, if you want to listen to the I1, all of a sudden what you have to do is you make sure that your C is 1 now. Then the output is going to be whatever the current value in your I1. So at any time you can change the focus to the I0 or I1 by changing the control value, control signal value. Okay, so that is how the multiplexer works, right? So you are getting so many inputs. In this case, two inputs. At any time, you can change or you can fix your output to get this value or this bit streams or this bit stream or this bit stream depending on the value of C. If it is 0, I0 is your output. If it is 1, I1 is your output. Okay, right? So you don't have to memorize the circuit, but you must appreciate and understand the idea behind or what is mean by multiplexer, how it is going to work, and also there are so many usages when it comes to memory management. We use multiplexers, right? Right. Now that is how the 2 to 1 multiplexer work. So same concept can be extended for 4 to 1, 8 to 1, 16 to 1, 32 to 1, etc. Right? So you don't have to memorize anything. But idea is now you need two input signals. Again, when both are 0, I0 will be your output, right? So there's a definite pattern. When both are 0, it is something like binary 0. 0, 1 means something like binary 1. 1, 0 means something like binary 2. 1, 1 means something like binary 3. So that is why we call them I0, I1, I2, I3. Someone might wonder why we call it I0, I2, I1 rather than I1, I2, I3, I4. So the reason is there's a definite pattern there. When both are 0, your I0 is going to be your I1, your output. When 0, 1, something like your binary 1, that is S0 is, that is why also the control signals are also called C0, C1 or S0, S1, because there's a nice number pattern there. When this is something like 1, but in decimal, your I1 is going to be the output. When this is something like 2, that is S0 is 0 and S1 is 1, I2 is going to be the output. When both are 1, that is something like 3, your I3 is going to be the output. So that you can always double check by substituting into this formula. Anyway, you don't have to memorize, right? So just understanding of 2 to 1 is enough, because then you must know that, okay, I can extend that to 4 to 1, 8 to 1, etc. Okay. Okay, now we are done with the multiplexers. Right? So now we are done with the adders. Adder is a completely different concept, but decoders, multiplexers, encoders, they are sort of a different type of category of digital circuits. Okay, but adder is a completely different thing. So these things are, adders are used for processing, whereas decoders, encoders, multiplexers have different usages. Especially multiplexers and decoders are used for communication, communicating a particular signal, right? So, but the adders are used for processing. So, adders are used in your processor, microprocessor, whereas multiplexers and decoders are heavily used in data communication. Data communication between processor and memory, or in networking, right? In networking as well. Right, now we are moving to the final one. Anyway, we are not going to go into details about the final one. So that is encoder. But for the completeness, we are just going to touch what is meant by encoders. Again, encoders are not difficult to understand. You can perfectly understand any encoder. Since we don't want to cover a lot of things and time restrictions, etc. In your syllabus also they have not mentioned much about encoders. Therefore, I'm not going to discuss. But if you want, you can go to the YouTube. There are so many tutorials that will explain you how the encoders are working. Okay, but I'm not going to details. I'm just going to explain just one type of encoder only, right? So first, let's try to understand what is meant by encoder. Remember, in decoder, we had 2 to the power n inputs and sorry, n inputs. Sorry, this. So in decoder, we had more inputs, that is, sorry, less inputs, that is n inputs, and more outputs. That means we want to enable one of the outputs, that is decoder. When it comes to encoder, it is something like the opposite. Here we have 2 to the power n number of inputs, more inputs and less number of outputs, that is n outputs, right? So here n inputs, 2 to the power n outputs, but only one output is enabled at a time. Here we have 2 to the power n inputs and n outputs, right? N outputs. So there is a difference between just by look and feel, that is the difference between encoder and decoder. So don't think that decoder is exactly the opposite or the reverse of the encoder, but it's something like that also, right? Right. So here there's a restriction again. Only one input line, right? Only one input line must be enabled O1. So that is very important. Remember, in decoder, only one output line is one at a time. Whereas in encoder, though we have so many input lines, right? Say 2 to the power n input lines and n output lines, only one input line must be 1. When this is 1, all the others must be 0. So that is that. So now you can see it's something like the opposite of the decoder as well, right? So you can say encoder, decoder are sort of opposite meanings. That you can see that resemblance is there. In decoder, only one output line is 1 at a time. In encoder, only one input line is 1 at a time, while all the others are 0. Okay. So therefore, you may consider it something like the reverse process of the encode decode as well. But the usage is completely different, right? But it looks like the sort of reverse process. Okay, now let's see just one of the encoders and see how it works. So there are different type of encoders for different purposes. Like we have the quaternary to binary. Quaternary means 4 to 2 encoder. Octal to binary or the 8 to 2 encoder. Hexadecimal to binary or 16 to 2 encoder. Then we have special encoders like decimal to BCD encoder, priority encoder, etc. Okay. So there are likewise different encoders. So we are going to discuss this just to get a feeling of encoders for you. Just one encoder we are going to discuss, that is quaternary to binary or the 4 to 2 encoder. Okay. So these 4 to 2 encoders, now remember decoders are used for what? When we want to send a enable one of the output signal with less number of input signals, right? So we have less number of input signals, lot of output things, but only one we want to enable at a time. Multiplexers means we have many input lines, but we have only one output line. We want to make sure that only one of the input is in the output now, or we have tuned to one of the input. Encoders are, the use of encoders is completely different. Usually we use encoders to convert one base number from one base to another base. Right? Number from one base to another base. For example, now let's see how the quaternary or the 4 to 2 encoder works. Its circuit is really funny, right? So it's actually really funny, and sometimes you get really confused when you see the circuit also. Right, so you can see it's very simple. Now you can see there are 4 inputs, 2 outputs. Only one of the input has to be 1 at a time. All the others must be 0, right? And there will be some combination here, right? So there's nothing says only one output is 1. Now it can be, we never know, 0 1 or 1 0 or both are 0 or 1 1. So now let's see for which combinations we are going to get these different outputs. Okay, so that is what we are going to look at it. Okay, right. So now let's see how the 4 to 2 encoder is built. 4 to 2 encoder is built using 2 OR gates like this. Right. So there are 4 inputs. Right. So I0, I1, I2, I3, and there are 2 outputs. Right. O0 and O1. And the funny thing is, your I0 input is not connected to anywhere else, or it's sort of isolated. And so that is where you get really confused at a time. We have our input, but it is not used even connected to the circuit. So that is really funny thing. Okay, but it makes sense. Right? It makes sense. Right now let's look at the uh, formula for the 2 outputs. For example, when you say O0, it is going to be I3 O I1 or I1 plus I3. You can see I1 plus I3. When it comes to O1, it is going to be I3 plus I2. Right? I3 plus I2. So that means O0 is right? O0 is I1 plus I3. O1 is I2 plus I3. Now if you draw the truth table for different I combination, now remember we have 4 inputs, I0, I1, I2 and I3, and we have now 2 outputs, O0 and O1, right? O0 and O1. Now you can substitute these different values, right, to these formulas and get the O1 and O0, right? Now if you substitute those values, for example say 0 0 0 1, in that case your I1 is 0, your I3 is 0, therefore 0 plus 0 is going to be O0 is going to be 0, right? Then here I2 is 0, I3 is 0, again 0 plus 0 is going to be 0. So that is why we got 0 and 0, both 0, right? Likewise, you can assign these combination to these formulas and you will get the O1 and O2 values, right? So once you get the O1 and O2 values, you will see a pattern. That is, when your I0 is only with, now remember, you can have only one value 1, right? So because that is how the encoder works. Just like your decoder, only one output is 1. In encoder, only one input can be 1. So therefore when your I0 is 1, whereas all the others are 0, then it is something like binary 0, 0 0. You know that 0 0 is 0, right? So it's something like your binary 0. When only I1 is 1, whereas all the others are 0, it is something like you have the 1 here. 0 1 means 1, right? When I2 has 1, all the others are 0, it is something like your binary 2, because this is ones, these are the 2's, it is something like your number 2. When your I3 is 1 and all the others are 0, it is 1 1. So that you have to get it from your substituting the formulas, it is 1 1. Right? Now you can see that this is really converting base 4 number, because assume that we have only base 4, that means 0, 1, 2, and 3 only, because base 4 the digits are 0, 1, 2 and 3. If you want to convert your 3 into binary, when you have I3 is 1, right, I3 is 1, all the others are 0, you are getting something like 1 1, that is binary 3 in binary. When you have 2, I0 I1 I2, you are going to get 0 1, sorry, 1 0. Likewise, when one of these input is 1, we are going to get a compatible binary number here. It's something like converting base 4 to the base 2, right? So you can see that though I0 is not connected to anywhere, it has an effect on the output. It has effect on the output because we are going to look at the overall the input combination, right? The overall input combination. Therefore, it has a little bit of a meaning, right? Little bit of meaning, and that is called a the encoder. So likewise, you can create just like 4 to 2 encoder, you can create 8 to 2 encoder, 16 to 2 encoder. Then there's a special case called priority encoder, right? So those things can be used for different. Actually, this is again mostly for processing and especially to conversion between the bases, right? Because we have to do some conversion between bases in the computer. Most of the time, people enter data in decimal, whereas we want to convert it to octal, hexadecimal, etc. And also we know that sometimes we can give color names in hexadecimals, etc. Okay, right. Right, now we are done with combinational circuits. We are done with combinational circuits. We have discussed the adders, we have discussed the decoders, we have discussed the multiplexers, and we just touch the encoder just to get a feeling of what is encoder is doing. Now you can see some devices are good for processing, some devices are good for data transmission, some components are good for some sort of conversions between bases, etc. Right? So all these circuits have different usages. Now we are moving to the second part of the circuit components, and we call them the sequential circuits. Okay, sequential circuits. So as I told you, what we have discussed so far is combinational circuits. You will see that you would have seen that none of those circuits that we discuss has memory. Or they are just doing some processing or converting or just conveying or sending a signal. Right? There's nothing called memory. But when it comes sequential circuits, we are going to see the concept called memory, or it depends on the current state or the previous state. Okay. So under sequential digital circuits, we are going to discuss two type of components called latches and flip flops. Okay, latches and flip flops. So both are sort of a memory cells, right? Both are active memory cells. So you have to first understand the difference between those two. Both can be used as memory cell. So when I say memory cell, a place where a single bit can be store, set, reset, invert, etc. Right? So when you take a memory location, say it's a 8-bit memory location, then you need 8 latches or 8 flip flops. Okay. So actually there's a small rain here. If you can't hear me properly, let me know. Okay? Right. So so when it comes to memory management, every memory cell is a latch or flip flop. Okay, every memory cell is a latch or flip flop. Okay, so just give me 1 minute. I will be connecting from the other room. Okay, because there's a lot of noise. Okay, so I'm back because there's a raining here. So I hope now the noise is little bit less at least. Now let's try to understand how the memory cell works. I hope you can hear me. Right? So if you can't hear me, just let me know. Okay. So I hope you can hear me properly. Right. Now let's try to understand how the memory cell works. So there are two type of memory cells we can create, either latch or flip-flop. Sometimes we use those two words interchangeably, but there is a small difference between latch and flip-flop. First we are going to discuss the latches, then we will be looking at the little bit of flip-flops. Okay. Again, we are not going to go into details because this is something to do with electronic, but we are just going to look at the overview only. Right. Now let's see. Uh, so when it comes to sequential circuits, so those circuits depends on the memory or the previous state. Right? Memory, we can call it either memory or we can just call it the previous state. And actually, most of these devices are used to keep the memory or retain data, retain data. Right. So those sequential digital circuits may be triggered in different way. For example, it might be triggered using events or clock driven, or that means it is triggered by the clock itself or pulse driven. So pretty much the clock and the pulse is sort of interchangeable words, right? But let's look at the, now as I told you, the memory cell means we must be able to set the value to 1, that is the memory cell is having 1. We must be able to unset the value to 0, that means at any time we must be able to change it to 0. When we change the value of a memory cell to 1, we say we set it. When you change it to 0, we say we unset it. Okay, so you have to understand the words first. And also it must be able to remember that one. For example, if it is something like this memory cell has 1 0 0 1, now it must be able to keep remembering this. So after sometimes also it must have 1 0 0 1. So at any time we can change it, but once we change it, it must retain it until we change it again or we delete it. Right? So it must be able to remember things or retain things. Remember, retain the values. Yeah, that is why we say it's a memory cell. Then optionally, we must be able to invert or the convert the value also. That means if it is 0, we must be able to say, okay, now convert, invert it to 1. If it is 0, change it to. So whatever the current value, change it. So that is optional behavior, but that is also handy. That is also handy if we can do that. So that means now we can set the, now memory cell must be, we must be, if it is memory cell, we must be able to set it. We must be able to unset it. It must be able to retain it, and we must be able to optionally invert it. That means whatever the current value is inverted to the other value, the opposite value. If it is 1, inverted to 0. If it is 0, inverted to 1. Okay, so those are the features we expect from memory cell, especially the first three features. Last one is sort of optional, it's additional thing. Okay. Right, now as I told you, either we can go for the latches or flip-flops to implement a memory cell. Right, we can either go for latches or we can go for flip-flops. Now let's first look at the difference between latch and flip-flops. Right, so when it comes to latch and flip-flop is the more sophisticated one. Right, more sophisticated one. Latch is the more basic one. The flip-flop depends on the clock pulse, whereas the latches does not depends on, though it is not synchronized with the clock pulse. Right? Both act as memory cells, but latch is less reliable, whereas the flip-flop is more reliable. Right? Flip-flop is more sophisticated, more reliable component. Latch is the more basic, sort of unreliable. When I say unreliable, less reliable component. But understanding latch is easier than understanding flip-flop. So therefore, we'll first try to understand what is meant by flip-flop. Okay? Sorry, what is meant by latch. And also you have to remember that sometimes flip-flops are also called gated latches. Right? Gated latches means it has more not security actually, more control over the normal latch. So therefore flip-flops are more reliable because it is sort of a gated latch, right? So it is more reliable, more robust kind of a memory cell. Okay, right. Now let's look at the latches, right? The simple one. Right, so we can identify, actually there are different latches, right? But most popular latches are the SR latch. Actually, this must be latch rather than flip flop, right? So actually, there's small mistake in my slide. It must be SR latch, JK latch, and D latch. Okay, sorry, I think I made a mess of this slide. I will just change it. So yes, so what we are going to discuss is actually SR latch, S dash R dash latch. Actually, there's a small mistake in this slide. So what we are going to discuss is SR latch and S bar R bar latch. Right. So there's a small mistake inside. So what we are going to discuss is SR latch and S bar R bar latch. When it comes to flip flops, we are going to discuss some other flip flops like SR flip flop, JK flip flop, D flip flop. But latches, we are going to discuss only SR latch and S bar R bar latch. Okay, so there's small mistake. Sorry about that. Okay, because I made that slides very hurriedly today itself. Okay, right. Now let's look at the SR latch, not the flip flop, SR latch. Okay, so this is how you draw the block diagram of the SR latch. So you have the S, two inputs, S and R, right? Then there are two outputs called Q and Q bar, right? Q and Q bar. Now there's definitely difference between latch and flip flop. I will just show it. Now here you can see there are two inputs, two outputs, SR, Q and Q bar. But if you look at something like flip flop, you can see there's a clock signal as well, right? So and it's more complicated, and there's something called clock signal. Okay, clock signal. So if you see something like this, that is clock signal, right? So you can see flip flops have clock signals, right? You can see here they say clock, right? Clock. But latches, they don't have the clock signal. But sometimes you will see that some people they just use these words interchangeably. For example, one person might say SR latch and SR flip flops as interchangeable names. So therefore, in that case, you might see the clock signal or you may not see the clock signal. But typically, latches we don't need a clock signal. In flip flops, you need a clock signal. Okay. But anyway, I also have made some small mistakes here and there. I will show those things. Okay. I have also put some Chrome diagrams here and there. Okay. Right now, let's try to understand the SR latch. Right. So remember, this must be able to set the value, reset the value. It must be able to retain the value, and optionally, if possible, we must be able to invert the value. Okay. Now let's see how the SR latch work. Now first let's look at the circuit diagram. It's sort of a very funny circuit diagram. It's sort of a recursive circuit diagram. Okay, so now you can see we have the R and S here. We have two NOR gates, right? And one of the input is your R. For the other NOR gate, the input is S. So when I say R and S, those are just our two inputs. We are just giving it the name R and S for some purpose. Then you have now remember we for a NOR gate you need two inputs. So the funny thing is the other input for the first NOR gate is the output of the second NOR gate, right? And the input for the second NOR gate is the output of the first NOR gate. Now it's something like sort of a recursive thing, right? So first one's output is the input to the second one, second one's output is the input to the first one. And here we have the Q and Q bar, right? So I'm just explaining these things to make sure that you have less to memorize, right? Because memorizing will, after sometimes you will get stressed out, right? Right. Now this is how it works. Now that is the diagram, right? That is the diagram. So the diagram I will explain a little bit later. But anyway, that is the diagram, right? So you have the two NOR gates. Each one is having one of the input as the input and the other one's output as the other input, and there are two outputs that is called Q and Q bar. Why we call it Q and Q bar is when Q is 1, always we expect that Q bar is going to be 0. When Q is 0, we expect that Q bar is 1, right? Q bar is 1. So then someone will ask, why do we need two inputs? So the way the circuit need to be worked, actually we need two outputs. Okay, so sorry, not two inputs, we need two outputs, but that must be always the opposite one. When Q is 1, Q bar must be 0. When Q is 0, Q bar must be 1. So that is why we call them Q and Q bar rather than output 1 and output 2 or whatever. Okay, so it must be the case, otherwise something wrong with the latch, right? If these things are both 1, right, if both 1 or both 0, that is your latch is not really working, but there is something wrong with your latch. Okay, it must be opposite values, right? So there is another point you have to remember about latches. Right, now let's see the truth label, right? So when both S and R are 0, we are going to see the no change in the output. That means whatever the output previously is going to be the same output again. That means when both are 0, if Q happen to be 1, and of course when Q is 1, Q bar must be 0. Now again, in the next clock cycle, in the next time slot also, it is going to be 1 and 0. That means if it is 1, it's going to be keep on 1, 1, 1, 1. If earlier Q is 0, that means of course Q bar is 1. When both are 0, it is going to be keep on when the time passed by, it is going to be 1, 1, 1, 1. Right? If it is 0, it is going to be 0, 0, 0, 0. That means it is remembering or retaining the value. So when 0, 0, we say it is the memory. Now things are getting remembered. Whatever the value is going to be retained. Right? Then when S is 0 and R is 1, our output is going to be reset to 0. So when we change the value to 0, we say reset. When change the value to 1, we say set. Right? Now you must understand why we call it S and R rather than A and B. When R is 1, your output is 0. That means we are resetting the memory cell. So right, so that means output is 0 means all of a sudden it is going to be 0. That means we are resetting. So how to reset? Make your R1 S0. So that is why we call this R, because when R is 1, you are resetting means you are making the output to 0. Right? So once you understand this concept, you don't have to memorize the truth table. You can just draw the truth table. Right? And similarly, when S is 1 and R is 0, that is S means the set, you are setting the output to 1. Right? You are setting the output to 1. That means you are setting the memory cell to 1. Right? So if you want to set, make sure that your S is 1, R is 0. If you want to make this 0, make sure your R is 1, S is 0. Right? So that is how you reset and set your memory cell. Okay? When both are 0, it is going to retain. If it is 1, it keep on 1. If it is 0, q, it is keep on remembering as 0s, right? But we have a special condition, that is when both S and R are 1. When both an S and R are 1, we say that it is illegal situation for SR latch. For SR latch, you can't have one situation. In that case, we say that our memory cell is sort of a corrupted or in an unstable or unreliable state. We never know what is going to happen. Or we don't know what is the value of this and what is going to happen. Right. So therefore, we have to make sure that in SR latch, we have to make sure that we never give 1 1 combination to the latch. Okay, 1 1 combination to the latch, right? So when S equal 1, we set it. When R equal 1, we reset it for 0. When both are 0, it is the memory. When both are 1, we must make sure that it never happens, because it results in a undefined state. Okay, now I hope you got a feeling of what is SR latch, how it works. Okay, how it works, and how why we have this terminology like set, reset, q bar, etc. What you remember is that if it is q is 1, always q bar must be 0, right? When q is 0, q bar must be 1. If both are 0 or both are 1, so that means it is again in an invalid state. Actually, what happens is, when if you set both S and R into 1, you are going to get this kind of a situation. So that is why we say don't make your S and R 1, both 1 at the same time, because it will result in both Q and Q bar in the same values. Okay, either 0 0 or 1 1. Okay, right. Now let's try to understand little bit, not fully, because fully understanding this truth table will take a lot of time, right? But at least at a sort of as a snapshot, try to understand how this truth table is made. Right. Right. Now you know that this is your SR flip flop. Right. This is our SR flip flop. So we have the R, S, Q, and Q bar. Okay. So as I told you, there are some combinations that will be making this set. Another combination will make it reset. Another combination, that is 0 0 combination, will retain it. 1 1, we don't want to make it happen. Okay. We don't want to make it happen. Okay. Now you can see what we have is two NOR gates. So therefore, let's first look at the truth table for the NOR gate. Right? Truth table for the NOR gate. So that is what you have here. Right? Truth table for the NOR gate. Okay. So because it's a NOR gate, it's not ON gate. In ON gate, sorry, not a O gate, it's a NOR gate. If it is O gate, when both are 0, only 0, otherwise 1. But because this is the NOR gate, when both are 0, only 1, otherwise 0. Because it's the inversion of it. Right? Otherwise 0. So what you remember is, when both are 0, it is 1. When at least 1 is 1, it is 0. And right, so that is what you have to remember. When at least 1 is 1, it is going to be 0. Right? So that is the most important thing to understand. When at least 1 is 1, your output is going to be 0 because it is no gate. Because in O gate, when at least 1 is 1, it is 1. In no gate, when at least 1 is 1, it is 0. Okay, right. Now let's see different combinations little bit, right? To get a feeling of how we are going to get this thing, because this is something like a very interesting. This is something like a chick and egg story, right? So whether the chick came first or the egg came first, because you can see this input is the output of the other guy, and also this input is the output from the other guy. So therefore, definitely it's something like a chick and egg story. So we never know which one is going to happen first, right? Right. Now let's see how it is going to understand. How we are going to understand it. Now let's assume we have set S0 R1, and we know that when we say S0 R1, we are what we are trying to do, we try to reset it, right? We try to reset it, or we try to make your memory cells value to 0, right? So when we are setting the memory cell to 0, we say that we are resetting. Now let's see whether it's going to happen, right? So now your S is 0, your R is 1, right? Your R is 1, and from this truth table you will see that when at least 1 is 1, right? When at least 1 is 1, these are the two inputs, it's going to be 0. It's going to be 0, right? Now already we see that now our R is 1. Now that is the case we are going to discuss. When R is 1, definitely when at least 1 is 1, the output is 0. Therefore this is going to be 0, right? When this is going to be 0, then this 0 is going to feed into this O gate, right? Now already this is 0. Now all of a sudden both are going to be 0 now, right? When both are 0, we know that the output is going to be 1. So therefore now here we are going to get 1. Now remember, this is 0, this is 1, right? So and this is Q bar. Now you can see that our Q is now 0, Q bar is 1. So Q is the one that we are interested. Q is 0 means now our memory cell is reset to 0, right? So that is exactly what the truth table says. When S equals 0, R equal 1, you are resetting, or you are setting the output to 0, right? Setting the output to 0. Now let's double check S0 R1, right? When S0 R1, you are resetting. Yes. Now we can see that is exactly what happened. That is exactly what happened, right? So now you have reset the memory cell, right? Reset the memory cell. Right? Now let's see what happen if you, right, what happens if you again make it to 0 0 again. Now we reset to 0. Now again, if we don't want to keep it we don't want to keep on resetting. Now we want to make it remember that it is 0. So how to make things remember? According to truth table, we have to make sure that both S and R are 0. Now let's see, when both S and R are 0, it is going to remember the things, right? Right. Now all of a sudden we are going to make S0 R0, right? S0 R0. Now remember, Q is 0, Q bar is 1. Okay, current situation. S is 0, Q bar is 1. Right. Now what we do, we make both S0 and R0. Both S0 and R0. Right. Now currently my Q is 0, Q bar is 1. Right. Because while after resetting we are going to make it both 0. Now since this Q bar is 1, now this 1 is fed here. Right. So when at least 1 is 1, we know that the output is 0. So therefore now this is 1, therefore this output is 0. Right? This output is 0 means the Q is 0, right? Q is 0. And also when this is 0, this is 0. When both are 0, the output is 1 and this is 1. Now you can see previously also Q was 0. We reset to 0. Now all of a sudden when we change it to 0 0, now it is keep on remembering that its Q is 0. Right? So we may set it to 0, and again by say, S0 R1, then we change it to 0 0 and let it remembering things. Now yes, it is remembering things. Now Q is 0, Q bar is 1, Q is 0, Q bar is 1. Now that is going to happen forever. As long as your S is 0, R is 0, it is going to keep all the time. Q is going to keep on 0 0 0 0, Q bar is 1 1 1 1. That means it is remembering that it is 0 now, right? So that is how we set, oh sorry, we reset the value in the SR latch. Okay, SR latch. Now let's see how to set the value to the of the SR latch. Now we know that setting a value means we want to make the memory cell have the value 1, right? Have the value 1, and according to our logic we know that setting the value means we want to make S1 R0, because S means setting, right? S means setting, right? So now we want to make S1 R0, right? S1 R0. That means we want to make our memory cell store 1. Previously we don't mind whatever you have, but we want to make it all of a sudden 1. Okay. Now let's again look at the truth table. We know that when we have a 1, at least 1, always output is 0. So therefore now here we have 1. We don't care whether this is 0 or 1. We don't care. This is 0. This is 0. And when this is 0, now both are 0. When both are 0, this is 1. Right? When both are 0, output is 1. Therefore now this is 1. Now when we set S to 1 and R to 0, now you can say Q is 1, Q bar is 0. Yes, that is what exactly we need. Now the memory cell is set to 1. Memory cell is set to 1. Now if you again release and let it remember things, now that means what? We are putting it back to S0 R0. Right? Now let's put it back to S0 R0. Right? Now remember, by the now when we are putting the 0 0, the memory cell was having 1, that is Q is 1. Now it will be fed here, right? Now this is 1, this is 0. Now when we have 1 here, output is 0, therefore this is going to be 0. Right? This is going to be 0. When this is 0, now both are 0. 0 0 means 1. Now you can see it is keep on remembering 1 1 1 1 1, and Q bar is keep on saying 0 0 0 0. Now we set it to 1 and put it back to the S0 R0 combination, and it is keep on remembering the 1 1 1 1. What we are interested in is the Q, not the Q bar, but we have to make sure that always Q bar is the opposite of the Q, right? Opposite of the Q. Now that is how you set the value to 1. Now we know how to reset the value, how to set the value, right? Right. But what we are not supposed to do is there's illegal scenario. And there's illegal scenario. Of course, the 0 0 we have already covered. The illegal scenario is what? Make sure that you never give it 1 1. You never give it 1 1, because it's going to have a adverse effect. Right? Adverse effect. So let's see what happens if it is both 1 1. That is, R is also 1, S is also 1. Right? We know that when at least 1 is 1, right, when at least 1 is 1, now output is 0. So that means here also it is 0, that is this one is 0. Now we can say this one is 1. Here also we have 1, this one is also 0. Now you can see our Q is 0, Q bar is also 0. So that is not going to work, right? So always Q bar must be the opposite of Q. So therefore we must never make both 1, because that result in a unstable situation or unreliable situation. Okay, so that is why, that is how you get this truth table, right? So rather than just memorizing, right, of course when the exam is nearing you have to memorize this, but if you have at least once in your lifetime, if you have understood this, it will be a much more easier experience rather than just remembering something you have never understood, right? Maybe you will forget it, but at least once in a lifetime you must try to understand this, so that you can appreciate this, and see that okay, so it's going to work, right? Because this is how your memory cells are working, right? So all your memory cells are either SR latches or JK flip flops. Okay, why this SR flip flops or JK flip flops. Okay, now I hope you got a little bit of idea about how the SR latch work, right? How the SR latch work. It's just two NOR gates connected together. And again, SR latch can be created in different ways as well. If you have two NAND gates, again you can create SR latch, right? So what I have explained you is the use of two NOR gates. Right now, let's look at the S bar, R bar, or S dash, R dash latch. The only thing is, now you have, rather than no gates, what you have is two NAND gates, right? NAND gates. So again, I made a small mistake. So forget about this one because there is no clock signal in latches, right? Because some diagrams they just miss it. So here we have the S bar and R bar, Q and Q bar, right? So it's very easy to understand. Remember the truth table. This is exactly the mirror image of the previous one. Remember 0 0 is the remembering. Now 1 1 is the remembering, whereas zeros 1 1 is the undefined. Now 0 0 is the undefined. 0 1 is the reset. It becomes 0 1 the set. 1 0 the set becomes the reset. Okay. Now therefore it's, you don't have to spend a lot of time, right? Now earlier, remember, when we say R, reset, but now R means set. That is why we say R bar. Earlier when we say S, set means 1, but now what is resetting, so that is why we say S bar, right? S bar means actually your S becomes 0. When it is 1, 1 bar is 0, actually you are resetting the data, right? So that is why we say S bar, R bar flip flop. And earlier 0 0 was remembering, now 0 0 is undefined state, right? Earlier 1 1 is the undefined state, now 1 1 is the remembering state. So it's exactly the mirror image of the SR latch is called the S bar, R bar latch. There you use the NAND gates, two NAND gates rather than two NOR gates. Okay, so that is how the S bar, R bar latch work. So it's very easy to remember the truth table, and also it's very easy, you know, that just change your NOR gates to NAND gates. So when it comes to flip flop, as I told you, it is more sophisticated than the latch because it has a clock signal and therefore it can guard against some undue effect. So that is why we call flip flops as gated latches. Gated latches. So we have, under flip flops, we have the SR flip flop, JK flip flop, and D flip flop. Okay, SR flip flop, JK flip flop, and D flip flop. So when it comes to SR flip flop, it is very much like your S dash R dash latch is there, right? S dash R dash latch is there. Then there are few more NAND gates. You don't have to memorize this. Actually, if you want to memorize, only you have to memorize the SR latch circuit diagram and S bar, R bar latch circuit diagram. You don't have to memorize anything else, right? But just you have to understand that there's something called flip flop. Now you can see clock signal is also there, and the truth table of SR flip flop is exactly the same as S bar, R bar latch. Right? So that is how what you have to remember, because this is the main latch here. This is just to guard against. So therefore, your SR flip flop is going to have the same truth table as S dash, R dash latch. Remember? So that means your SR latch and SR flip flops are going to have two different truth tables, because S bar bar truth table is going to have going to be your SR flip flop truth table, right? So then we have the JK flip flop. So the JK comes from the two people that invented this particular flip flop, Jack and Kilby. So they are, again, we have, rather than S and R, we call them J and K, and we have the clock signal. You don't have to memorize the, anyway. If you can remember, you can just remember it. But the truth table is again same as SR latch. Only thing is, in SR latch, 1 1 resulted in undesirable or unstable state, whereas in JK flip flop, your 1 1 can be used to invert the value. If it is 1, it will be inverted to 0. If it was 0, it will be inverted to 1. So now that in SR latch, 1 1 is a dangerous situation. In JK flip flop, 1 1 also we use for some purpose to invert. So that is the thing that you have to understand when it comes to JK flip flop. So actually, the most popular flip flop is the JK flip flop because it is more versatile, and of course it's a flip flop, not a latch. It is more reliable. Okay. Right. Then we have final one more flip flop called D flip flop, or the data flip flop. It's very simple one. The outcome actually it is sort of a combination of S bar, bar latches, etc. Where we have the D value 1 and 0. When D is 1, we say set it. When it is 0, we say reset it. And actually there are some complicated scenarios. We are not interested. Just remember there's another flip flop called D flip flop. Okay, right. So this is the sort of a summary. You have to look at all these things at the same times. SR latch, S bar R bar latch, which is the mirror image of SR latch. Then the SR flip flop is same as S bar R bar latch. JK flip flop is pretty much your SR latch, but only thing is here there was an undefined state. Now we are using it for something else. So likewise, don't fear, don't get feared that I want to look at all the things at the same time. That is how you must look at it. Then you will see the connection between those things, right? So you can see this is the mirror image of this one. S because that is S bar bar latch. Then the JK flip flop is just the SR latch. Only thing is this undefined state is now used for something else. And also if you want the SR flip flop is same as S bar bar latch. Okay, so that's it. You have what you have to understand. Right now we are done. We will briefly look at few usages of digital circuits as well. Then we will move on to some faster questions. Right, so this is your memory organization. So now you can see these are the latches or the flip-flops, right? So because these are set actually memory cells. So if you take memory location, there will be set of latches or set of flip-flops. And now when we want to enable one of the memory cell, we can use decoders. As I told you, when you have 20 blinds, I can enable one of the 2 to the power 20, that is over 1 million memory locations. So therefore, the computer is going to use decoders, right? Then using few lines by combination of different 0, 1 values, we can say exactly, yes, I want to read this one. I want to write to this particular memory location, etc. So you can see decoders are used, right? And again, when we are reading the data, we can use the multiplexers because each of these lines are connected to a multiplexer, right? But at a time we want to read one of the memory cell, one of the memory cells or one of the memory location. In that case, using control signals, we can enable and say, okay, I am interested in listening to this particular output, this particular input as the output, right? So you can see in memory accessing, so as an input we use decoders. When we are getting output or reading values, we use multiplexers. So that is one place where the decoders and multiplexers are used. And of course in the networking also we can use, but this is one place where in the computer memory management or memory accessing we can use decoders and multiplexers. Okay, right. So then this is a very simple ALU. Actually, this is a 2-bit ALU, which is given in your reference book. I am not going to discuss this because I have uploaded another, because I did this exactly same session when I think about May or April, while the lockdown is happening for you guys. Some of you have attended to that one also. There I explain all these steps, how this mini ALU is working, because it's very important to understand how the ALU is working. This is just a mini ALU, consists of 2 bits only. So it is in the YouTube. You can have a look at that. Maybe the last 15 minutes I explain how this is working. So therefore I am not going to explain it again. If you have the curiosity, if you are interested how the ALU work, right, as this as a prototype, because you know that ALU can do arithmetic as well as logical operations, right? So this particular simple ALU can do the logic operations and add operations. So of course this one has not incorporated any subtract multiplication. This is just to demonstrate how a simple ALU work. Okay, so I'm not going to explain it because it is explained, but it's a highly optional thing, right? If you are really interested in those things only, you can go it. Otherwise, you can just forget about it. Okay, right. Right. So that's it. Now let's try to do at least few past paper questions. Actually, you don't get much questions from this section. Right? Most of the questions are from the the previous sections. This is but in the future you will get a lot of questions, because in the A-level ICT also now they have added adders, flip flops, all those things they have added to the A-level ICT as well last time. So that means this is your degree level, so they are going to ask a lot of questions in the future in the encoders, decoders, multiplexers, etc. uh, right. So things are getting we are now getting little bit depth into the topics, okay, because if a student can understand the latches, they can understand the full adders, decoders, why can't you understand? You are in degree level. Okay, right. So let's do few past paper questions. So if you have any questions you can ask, right? Otherwise, I will just pick few past paper questions, and at any time you can post any of your past paper questions or any other questions to the WhatsApp group. So let's try to do few more questions and finish the session. So the next session we are going to look at the computer architecture, different architectures, and how the memory management is done, and we are going to finish the big topic. Then it's just simple theory parts are there, like input devices, output devices, etc. Okay, so the next topic is going to be really critical topic, because a lot of questions will be from there: the computer architecture, RISC architecture, CISC architecture, pipelining, and also the memory access, memory management, memory address translation. So we are going to discuss in the next topic, next session, probably next week. Right. So let's try to do few questions, at least just one more paper. So let's take 2018 paper, because I think we discussed 2019 paper last time. Right. So question 13. Consider the following Boolean function. So when you are doing these kind of questions, the first thing is you must know those rules. Okay, so you must know those rules. Otherwise, it will be little bit difficult for you to do it. Okay, so very good thing is when you have free time, take a piece of paper, right? So write all those 20, I think 23 rules are there, right? So anytime I can write all these 23 rules, so that must be the case for you also. So for example, so let's try to write those things just once. So say you can start from whatever you want. I will go for something like, just I will quickly write all the things. It won't take more than 1 minute. A bar bar is A, 1 bar is 0, 0 bar is 1, and also A dot B is same as B dot A, and dual A plus B is same as B plus A dot B dot C is same as A dot B dot C, then the dual A plus B plus C is same as, it doesn't matter where which one you O first. Then something like in algebra, expanding the brackets, A dot B plus C can be written as AB plus, when I say AB, A dot B plus AC, then the dual of it, A plus B dot C can be written as A plus B dot A plus C. Then you have the De Morgans, and then you have De Morgans. A dot B dot whatever bar is A bar plus B bar plus, then the dual of it, A plus B plus bar is A bar dot B bar dot, right? Then you can play A with A with A bar, A with 1, A with 0, right? A dot A is A plus A is A. So when I say A dot A, I always remember A intersection A is A union A is A. Right? So likewise it comes to my mind. Then A dot 0 is 0. It's something like A intersection 5 is 5. And then A plus 1 is 1. It is something like A union universal set is the universal set. Right? So likewise, I have so many ways to understand this. So then I never forget these things. Then I can again play with 1 and 0 differently. A dot 1 is A plus 0 is A. Right? So it's something like A intersection universal set is A. Remember, when you have A intersect with universal set, so the intersection part is A. Right? So likewise, if I forget it, I have so many ways to access and just remember it again. Right? So then you have the special cases uh, like A plus AB. This is the most widely used one. A plus AB is A. A plus A bar B is A plus B. Similarly, we have A plus B dot C plus D equal AC plus AD plus BC plus BD. And finally, you have the exclusive O. We can transfer to and NOS and not. That is AB bar plus A bar B. If you don't remember these things, you are in trouble. Right? It's not good for your confidence, and also you might feel like okay, either when you are not remembering all the rules, you will feel like actually it's not good for your confidence. Sometimes you are reluctant to solve it because sometimes you feel like okay, there may be some rules I don't remember, right? So these are not difficult because all are duals. So these are duals. Right? These are all duals. Once you have write one, we can always get the other one. So here also dual. So these are just again separate parts, right? So just change dot to plus, 0 to 1, 1 to 0, and you are getting the dual. Right? So therefore, don't think that this is a large number of things. These are just few things with duals. Okay. Right now, let's do this paper because without no remembering these things, it's not going to work. It's not going to work. Right. So let's see this. Right. Let's try to expand this one because we don't want to draw a Carnot map or whatever. And anyway, it's a mixture of things. So let's try to expand this using the rules. And also, I want to do it in a very smart way without, if I can see something very easily simplify, I will go for that. Okay, so I will go for some, I will do it here itself. So here I will say AC, right? If I can't figure it out, I will again try out new thing. AC plus BC. Now let's see, you can see here there's a block. So that now rather than simplifying like that, I think it's going to be easier. Right? So likewise, don't just blindly start. Yeah, I will take this one and this one. Then you have to think in blocks. Okay. When I say A, I can take A plus B. Then it will be C plus C bar. So I like C plus C bar because I know that A plus A bar is 1. Right? It's something like uh, E or not T. It's tautology, right? You have done the truth logic in maths as well. So here we have the, I don't know what is this, A, B bar and A bar B. So let's keep it. Let's just keep it. A, B bar plus A bar B. But definitely this is 1 and something dot 1 is something. So therefore this is A plus B plus AB bar plus A bar B. Okay, now I like to take this one and this one together because then I can take A out, that is 1 plus B bar, plus I will take these two together so that I can take b out, because a bar b I can write it as b a bar. Remember, a dot b is same as b dot a. Then I have 1 plus a bar. Right? So I don't mind whether b bar or whatever. 1 plus something is always 1, because in all logic, when something is already 1 or when something is already true, the entire thing is going to be true. So therefore this is a dot 1, and we know that a dot 1 is anyway a, and this is b dot 1, and a dot something is a, and b dot something is b dot 1 is b, a dot 1 is a, b dot 1 is b. So therefore answer is a plus b, the answer is a. So likewise you must be able to uh, keep on simplifying, but look for the patterns and think in terms of blocks. That those are the key things. Think in terms of blocks. Don't just start expanding. Look out for the possible simple simplification scenarios. Okay, now let's see whether the answer is correct. 13, this is 2018. So the answer is A. Answer is A. Yes, answer is A. Right. So I hope you got it. If you have any questions, you can ask. Now let's look at the second one. So second one is not a difficult one. So it just say which of the following Boolean function provides simplified form of f. Now again look for the bar values, etc. Okay. So rather than simply doing it, otherwise we can quickly draw we can even quickly draw a Carnot map and simplify it if we are lost, right? So here the values are x bar y plus xy z bar plus xy z. So let's try. If you take y out, it will be, but here you can see both xy can be taken out, so therefore this is better combination, right? So likewise, just be patient, don't just rush through. So I think this is better, right? I will just keep this as one as it is, x bar y plus I will take xy out, then z bar plus z or z plus z bar, it doesn't matter because a plus b is same as b plus a. That is one of the rules we have discussed, and z plus z bar we know that is 1, and something dot 1 is the same thing. So therefore we have x bar y plus xy. Okay, now I can take y out. Now I can take y out. I can, if you want, you can write like y x bar plus y x, because a b same as b a. I will take y out. That is x plus x bar or x bar plus x. And x plus x bar is, we know a plus a bar is something like a union not a, and that is entire thing. Okay, so whatever way you can remember, x plus x bar is 1, y, right, 1, y dot 1 is y. So the answer is C. The answer is C. So let's see the answer. 14th. Yes, answer is C. Right. So now let's look at the 15th one. The following figure represents a logic circuit. Which of the following logic circuit provides similar output to the above circuit by implementing solely? Solely means only with NAND gates, right? Only with NAND gates. So this kind of question we did last time also, right? So first we have to know that using AND gate, NAND gates, how to make an AND gate, using NAND gates, how to make an OR gate, and also using NAND gates, how to make a XOR gate. But don't do it as it is. First do some simplification and see whether you can come up with a better simple solution. Okay, so let's first write down this expression. So this is what we have is a NOR gate, and what we need is NAND gate. This is basically A plus B bar. Here we have B dot C. b dot c. Okay, so then we have to and it, and it. Right? So when it, remember when it comes to NAND gates, we don't like OR gates. Right? We don't like OR gates because OR gates need lot of NAND gates. Remember I discussed that last time. So that I discussed last time also. So we don't like OR gates because OR gates need lot of NAND gates. So this is what we did last time. Right now you can see OR gates need 3 NAND gates. Right? So what I like is lot of AND gates, NAND gates, NOT gates. Right? Even XOR gates I don't like. So therefore let's try to refine this. Let's refine this. Remember the strategy I explained last time? When you have this kind of situation, make sure that you apply this one, you write it as bar bar. So that is exactly what I did last time also. I'm not going to do different things at different days. I told you when you have something like this, make sure you write like this because when you have a, writing a bar bar is not going to change because we know that a bar bar is a. Then apply the De Morgan law here. This is exactly what I did last time also when we were doing the 2019 paper, right? So then apply the De Morgan law. Then it will be a plus b De Morgan law means a bar dot b bar. So this block, that is a plus b bar bar dot bc bar, and the bigger bar is still there, right? So then it will be a plus b dot bc bar, okay, bc bar, but still we have o gate, right? Still we have o gate. So can we do something for that as well? Shall we write this as well, a bar, a plus b bar bar, and let's see if it is possible. Otherwise we have to do something else, right? So I'm from here, I'm going to here, a plus b, I'm going to write this as bar bar, okay, dot, I'm not changing anything, bc bar, that big bar is there, okay. So if I write this, then I can apply the Morgan law, that is a bar dot b bar, and the upper bar must be there, dot bc bar, then we have the bar. Now for this one I need an AND gate, right? So here I need not another NAND gate and another NAND gate. Now you can see a lot of NAND gates I need. Right? So I'm giving the same sort of it's like a doctor giving looking for the symptoms and giving the correct medicine. Okay, so I don't like O gates. I don't like O gates because O gates consume a lot of NAND gates. Okay, right now let's see whether that is there in our answers. So definitely we need BC bar. So BC bar means just one NAND gate. BC bar. Yes, this looks like the BC bar, right? Then this is A bar, right? A bar. We have to not, now you can see this is, okay, so this is A bar, this is B bar, this is A bar, B bar, bar. Now you can see this block is this block, right? And this is BC bar. Now you can see this is B coming, C coming, this is BC bar, right? So this, now this is BC bar, right? So that one, and this is A bar. Remember A bar, using NAND gate you can create a NOT gate. And this is A bar, this is B bar, and therefore this is A bar, B bar, bar, right? So that one. Then this big NAND gate is there. this big NAND gate. So that one and that one and not. So that is your this big NAND gate. This block, this block, this. It looks like A is correct. It looks like A is correct. And because it's taking a lot of time, I don't want to look at the other one. I think others are not going to work because I can't look at each and every one and say whether it's correct or wrong. But it looks like A is correct, right? Usually in this kind of question, you get only one answer correct. So let's wish some luck and see whether the answer is correct because I don't want to spend too much of time on this kind of question. If I have time after doing all the other questions, I will revisit this question and see whether is there any other answer. Okay. For the time being, I will go for A. Right. So now let's see whether 15 question. What is the answer? Whether it's A. Yes, answer is A. So usually this kind of question you get only one answer. Okay. Right. So don't spend too much of time also. Right. So usually here, once you follow that rule, usually you get one simple because it's because others are even simpler. Right. So I don't see any way I can make it even simpler. Right. So that is why I took that decision saying that okay, this might be okay because these are even simpler. I don't see that it's going to be that simple. Okay. Right, now let's move on to another question. So I didn't do anything other than what I explained last time. There also I did the same thing. I apply the Baba, right? Then apply the De Morgan law. Here I did it again because again I see there's a O gate. I don't like O gates because O gate consume a lot of NAND gates, right? So therefore I again did the same thing, right? So the same medicine I used twice here and also here, right? So that is the same medicine I used last time for the 2019 paper as well. Okay, right. Now let's see another question. Right, so that is a Carnot question. What is the most compact form of Boolean function which represents the Carnot map? So I will quickly. So in that kind of situation, you better bring a pencil so that you can do that in your paper itself. So that will make some time, right? Otherwise, you are wasting time. Now remember what are the rules? You have to go for the largest area. It must be square or rectangular space. It must have only once, right? And also overlapping is allowed. And also the topmost and the bottommost are consecutive. Leftmost and rightmost are consecutive. Now let's try to figure it out. What are the regions? Okay. So I don't see any 8 region, right? 1, 2, 3, 4, 5, 6, 7, 8. But there are no 8 regions. But definitely there's a region of 4, right? So what is that? This is the region of 4, right? This is the region of 4. Then you have to keep looking for region of 4s. If there are no regions of 4s, only you have to look for the regions of 2s, right? So definitely I can see another region of 4, that is these two and these two. So I can't go for region of 6. Then again I can see a region of 4 rather than region of 2, that is this one together with these two, sorry, these two, and also it has these two. Now you can see it's again region of 4, right? Region of 4 because there are no regions of 8. Now I can quickly write the expression for each region. I will take this region first. If you can just look at it and tell that it's perfectly okay, but I will write it A, B, C, D so that I don't want to make any mistakes. It's always A, B, C, D. That means so this one is 0, 0, 0, 0. Second one is 0, 1, 0, 0. Third one is 1, 1, 0, 0. Fourth one is, that is this one, 1, 0, 0, 0. So you can see the C and D, they haven't changed at all. So that means there we get C bar, D bar. Now I am done with one. Now I will be looking at these 4 corners, A, B, C, D. So this corner is 0, 0, 0, 0. And then this corner is 1, 0, 0, 0. Then we have this corner that is 0 0 1 0, and we have finally this corner, that is 1 0 1 0. So again you can see this line is there, this line is there, both are zeros, that is b bar d bar. Now we have one more region, that is these two and the other two, a b c d, 0 0 0 0. This one is 0 0 0 1, 1 0 0 0. This one is 1 0 0 1. You need a lot of patience. Right? So again you can see B and C have not changed and they are zeros. Therefore I will go for B bar C bar. And answer must be B bar C bar plus B bar D bar plus C bar D bar. Right? Now let's see whether we have answer like that. Right? B bar C bar, B bar D bar, C bar D bar. So the answer is A. Answer is A. Now let's see whether the 16th answer is A. Yes, 16 answer is A. Right? So if you do it systematic way, usually you don't have to worry. Right? But if you are very careless, if you don't have systematic way, right? So you just feel like it might work. No, you must have definite systematic approach. Right? So then you know that I must get the correct answer, nothing else. That is the kind of people we want to be software engineers. That is the kind of people we want to be a doctors, right? So take responsibilities, right? Not just doing for the sake of doing. Right. So this one I'm not going to do. This is very easy question. So just substitute and see which one is you are getting for C. Okay. Right. So then we have another question. How many NAND gates are required for the logic function if it is to implemented using NAND gates only? Right. So yeah, so NAND gates only. So again you can see there are O's. I don't like O gates, therefore I am going to apply that bar rule. So okay, bar rule. Now let's see whether I will get the same answer as the examiner. So therefore what I am going to do is I am going to apply the A bar is A. Okay. So then I am going to apply the De Morgan rule. So same thing I am always using. So then C A bar dot B C bar dot, I don't know where is this bar, whether it's only for B or for both. So that is the issue with your papers. I assume that is only for B. Okay. Right, I assume it is only for, yeah, yes, no, I think it's both AB. I think that is why I have this note here, because it's not clear. I think that is both for A and B. Okay, so AB bar, then AB bar. Right, so if it is not clear in the exam, I think you can even ask from an instructor there, saying that this is whether it's AB bar or whether AB bar or AB whole thing bar. It looks like it's AB whole thing bar, but I'm not sure. Okay, right. So let's assume that is the case. In that case, now how many we need? And of course, the big bar is still there. The big bar is still there. Right, now let's see how many NAND gates we need. So for the NOT gate, I need one because there's a NOT here. I need one. For this entire NAND, I need another one because NAND I need one NAND gate. For NOT I need one NAND gate. For this NOT I need one NAND gate. For this NAND, once I NOT it, I need another NAND gate. Now 4. So this, if it is bar, this is going to be AB, right? AB. I'm not sure if it is only B bar, my answer is going to be different, wrong, right? Because I'm not very sure. I think it is AB bar. Now that means AB. Now for this is AND gate. For AND gate, I need two NAND gates because I have a NAND then I have to note it again. I know that how to note it, right? So just use another NAND gate. Therefore, here I need anyway two gates, right? So that is for AND gate. I need two NAND gates. We explained those things last time. And assuming that this is a big NAND gate, you can always assume that there are three NAND gates, right? This is three input NAND gates, right? So for that, in exams, usually you can assume that you just need one, right? So that is big NAND gate with three inputs. Now, if so, how many NAND gates we need? 2, 3, 4, 5, 6, 7 NAND gates are needed. Right? 7 NAND gates are needed. I assume that we have this kind of an NAND gate. Right? So usually you can assume like that. Okay. So in reality, actually, you need two NAND gates. Right? This one and again you NAND like that. But usually you can assume that that is just one NAND gate. Okay. NAND gate with three inputs. In that case, for me it is 7, but my answer will be wrong if the question is just A B bar. Okay. So let first see whether the answer is correct. 18 question, whether it's C. Yes, 18 question is C. Right? It's C. I think my question anyway. If it is A B bar also, it's going to be the same thing. Right? Right. A B bar also, yes. I think yes. That is also we are going to have. We can do it in two gates because one for the bar, other for the NAND. Yeah. So whether A whether that value is that is the doubt we are having had whether it's a b bar or whether a b bar, it doesn't matter always. In both the cases we need just two NAND gates, right? So those are the logic questions they are having, right? So those questions are not difficult. You can see none of the questions are from what we have discussed today, because in some years only they ask from latches, etc. Okay, right? So maybe just briefly look at another paper, but I am not going to do each and every question. Maybe just randomly pick one question. Or if you have any questions, you can ask. Right? So I ask you to put up those questions. So you must be proactive people, right? Right? Engineers must be proactive people. They don't wait until things are happening. They make things happen. Right? They design things. They solve problems. So they must be proactive. Right? So these are pretty much the same kind of questions, right? So I don't see any reason why you can fail this subject, right? So you must be given a sort of a medal if you fail this subject, right? So no, I don't see any specific question. Okay, so then if you have any questions related to logic or whatever, you can ask, right? So next time we are going to a very important topic, computer architecture. A lot of questions are from that. So all these questions like these memory calculations and those things, these registries, architecture, we are going to cover in that particular topic. Okay, so we'll stop at this point. So hopefully next week we can do the rest of the other topic, that is the computer architecture and memory calculation, etc. Okay, we'll stop at this point. Okay, thank you.